Good evening, everyone. So I'm going to present on this topic of optical microscopy. So these are the contents that I'm going to cover in this presentation. I'll start with an introduction. Then I'll move to the principle of light optics, what really goes behind these microscopy techniques, the various components in a optical microscope, some technicality involved, then microscopy techniques, different microscopy techniques, for image acquisition. Then I'll end this presentation with applications and certain advancement in this field. So to start with, optical microscopy is a technique employed to closely view a sample through the magnification of a lens with visible light. So particle down to the size of 0.4 to 0.7 micrometer in diameter can be seen under optical microscope. Image from an optical microscope can be captured by normal light sensitive camera to generate a micrograph. So generally it acts in the region of the visible light wavelength. So and this is how what a typical microscope optical microscope looks like. So what are the main principles behind the light optics? So one of the major thing that goes inside a microscope is the reflection of light, the bending of light as it passes from one medium to another with different refractive index, enabling the magnification of small objects. Then diffraction, scattering of light occurs, spreading of light waves around obstacles, which can create interference patterns in image, affect image quality. Then there is also aberration, that is nothing but the imperfection in the optical system, which can distort an image, such as spherical or chromatic aberrations. So these are the principle of the main optical physics that is going inside a optical microscope, and that's how we get a picture of an enlarged image of an object. So the main components of an optical microscope are like somewhat looks like this. So there is an eyepiece. It's an lens through which we look. This part is used to look at the specimen. These lenses come in different magnification powers from 5x to 30x. But the most common ocular lens are of 10x or 15x magnification. Then below the eyepiece, there is diopter adjustment. So it's a control knob present only in the binocular microscope that is used to change focus on one eyepiece. So it is used to convert to correct any difference in vision and compensate for the difference in vision between the viewer's two eyes. Then after that, the objective lens comes. These are the lenses which captures the light which comes from below here, transmit through the specimen. It is captured by the objective lens here. A standard microscope has 3 to 4 objective lens, different magnifying power, 4x, 10x, 40 or 100x. And these objective lenses are color coded. So their power are generally identified by the color code is present in the lenses. So the smallest lenses is of lowest power and the longest will be of the highest power. The high power lenses are retractable. That is, their end can be pushed inward and outward. In most optical microscope, objective lens with 100x or more magnification are of oil immersion type. Then comes the adjustment knob, fine adjustment and coarse adjustment knob. So these adjustment knobs are present here. This is fine and the coarse adjustment knob just used to adjust or move the stage very slowly by the fine adjustment knobs, and the coarse one moves the stage rapidly up and down. Then in stage, this is the section where the specimen or the sample is placed for viewing. They have stage clips to hold the specimen slides. Then also stage control nodes there. These controls move the stage mechanically left, right, or forward or backward. Then there is aperture. This is nothing but a hole, small hole in the microscope stage through which the light coming from the source is transmitted. It comes from the aperture and reaches the stage and illuminates our sample. Then illuminator is the light source. It's a compound microscope and mirror reflects the light uh, reflects the light into the sample. Then other optical various other illuminators are used in optical microscopes. Commonly used are halogen lamps, xenon lamps, dim light lamps, mercury vapor lamps, etc. Okay, then there is condenser. So these are the lenses that are used to collect and focus light from the illuminator. So the beam of light that is coming from the light source is condensed by these lenses to direct it towards the specimen. It plays a major role in ensuring clear, sharp image with a high magnification up to 400x and above. And there is diaphragm or iris. It is found under the stage of microscope, controls the amount of light that reaches a specimen. So the amount of light that reaches the specimen, its intensity also matters when it comes to uh, developing a clear and magnified image of our specimen. So it controls how much light to be passed through and how much to reach the specimen. Then condenser focus knob, it moves the condenser up and down, thus controlling the focus, the light on the specimen. There is gate condenser. This condenser specifically designed for high quality microscope, very high magnification, where high magnification is required, like 400x. And there is rack stop. This limits the movement of our stage in the microscope. So a bit of technicality inside a microscope. So the resolving power of microscope is the smallest separation of two objects. So if a microscope has high resolution, it will be able to differentiate very closely spaced objects. It will be able to differentiate those objects very clearly. So this resolving power is given by 0.61 lambda by n sin alpha. Here n is the refractive index of the medium where object is immersed. Alpha is the maximum half angle subtended at the objective lens by the object. So by this object, it is half of the angle here, which is created. And this product, n sin alpha, is called numerical aperture of the objective lens. And the main variable here is the lambda. That is the wavelength of radiation used. So what are the main optical microscopy techniques currently used? So there are many ways that the light path can be modified to improve the contrast on the image of a sample. So there is cross polarized light illumination, bright field illumination, dark field, phase contrast illumination, differential interference contrast illumination. So this cross polarized or there's a different type called a reflective microscope. These two comes under bright field illumination technique only. So what is polarizing microscope? So it contains a polarizer, and a polarizer allows light components which is vibrating parallel to the polarizer. So it only allows the components of the light which is vibrating parallel to it. So the light which pass through it reaches the lenses, aperture, and other accessories, and is focused onto the sample. So the light transmitted by the sample then immersion liquid is picked up by then it is picked up by the objective lens. Then there is another thing called analyzer, which is similar to polarizer, but it is placed at an angle 90 degree to the polarizer. So the analyzer is similar to polarizer in its vibration direction is at 90 degree to that of the polarizer. So there are also different functionality involved with this analyzer. So in a different setting, when the analyzer is out setting, then the instrument simply acts like a magnifying instrument. With that, we can examine the shape and size of the particle in the specimen. And when the analyzer is in, the sample is viewed between cross folder. Then with that technique, we can simply identify various crystals as isotropic or anisotropic. These isotropic crystals can look like dark. These are for cubic crystals or purpose. Then anisotropic are observed as bright or colored crystals. These are non-cubic crystals. So what I mean by this dark isotropic crystal is that when isotropic crystals are placed and looked through the polarizing microscope, it appears dark. It appears dark between cross polars since plain polarized light passes through them without modification. So the light passes through the those isotropic crystals directly um, without any modification. So the light is cancelled out by the simultaneous action of polarizer and analyzer. But in case of anisotropic crystals, those crystals causes partial rotation of the plane of polarization of the light. So when a particular component passes through the polarizer, then it reaches the anisotropic crystal. Then those crystal causes a partial rotation on that component of the light. Then that rotated light can be allowed to pass through the analyzer. So whole light is not blocked out. If part of the light is allowed to pass through the analyzer, that's why those crystals appears bright or colorless. And those are identified as anisotropic crystals. Uh, those are basically non-cubic crystals. So other applications of this microscope involves phase diagram studies. Limited number of phases are likely to appear. Then we can check the purity sample, provided that the impurities forms a different phase than our sample of interest. Then classification of anisotropic crystals into uniaxial or biaxial, depending on the optic axis, can also be done with this microscope. Then other kind of bright field microscopy is reflected light microscope. Here, if the light is reflected off from the sample or specimen. Here, the source and the objective lens are on the same side of the sample. So this is a normal microscope, and this is a reflective microscope. Here you can see the light source and the objective lens is on the same side, this upward side of the specimen, but here it is different. So reflected light microscope is used to examine solid lumps or opaque material such as metals, minerals, or ceramics. Provide information regarding the texture of the solid, that is, phases present in their identification around morphology. In reflected light microscopy on polished and etched material can provide much information on the internal crystal surface. Example, the grain boundaries or the line defects are also identified with this microscope. So electron microscopy also kind of like acts similar to optical microscopy, but the only difference is electron is used instead of light to interact with the sample or the specimen. So basically, it works on the principle of transmission, where the beam of light or electron in case of electron microscope is allowed to pass through the specimen in case of transmission, and it is reflected by the specimen in case of reflection principle. So the polarizing microscope is a transmission instrument used by geologists and mineralogists. Samples are usually transparent, fine powders and small slices, and light is transmitted through the sample by immersion in a liquid whose refractive index is close to that of the sample. And the reflected light microscope is a reflecting instrument, as the name suggests. Light is scattered off the sample, suitable for looking at the surface of material, especially opaque samples, metals, used in metallurgy, mineralogy, or ceramics. So as I mentioned before, the bright field microscopy is a broad term under which the microscopy that I explained before comes under. So this is the simplest technique, most straightforward technique used, may be used in the research and medical field to view biological tissue samples. So here the illuminator or the light directly is focused under a sample. So the light gives us a bright background, and against that we need to look at the sample, uh, which appears dark. So for that we need to really stain the sample so that it forms a good contrast, so that we can identify the different the boundaries and the shape of the sample against the bright background. So for this, we usually it really requires a stage sample. But if we want to, if we want to acquire a clear photomicrograph of living cell without the necessity of staining, then bright field may be not suitable, then we can go for dark field. So in dark field, as the name suggests, the background is very dark, and against that we look at the sample which is bright. So the difference is that it uses a dark field stop or a dark field filter to stop the beam of light directly coming from the light source. Here you can see the light source is blocked by this filter here, and only the oblique illumination is allowed to pass through here and reach the specimen. So this blockage creates a dark background, and this reflected light uh, illuminates the sample uh, for us to look at it. So when the numerical aperture of the objective lens is less than 1, dark field filter is used, that is positioned just below the subscript condenser or above the base illuminator. Already mentioned, the dark field microscope uses specialized illumination technique that blocks the direct light and allowing only the scattered light to reach the sample. So here's the difference, clear cut difference. Here we can see in bright field microscope, we are unable to correctly differentiate between the foreground and the background, or circle and the background, but in uh, dark field, we can clearly identify the sample from the black background. There is other technique called phase contrast microscopy. It works in the principle of interaction of light with medium that causes the wave amplitude and phase to change in a manner dependent on properties of medium. So this change in amplitude or the brightness arises from the scattering or and absorption of light, which is often wavelength dependent and may give rise to colors. Phase contrast microscopy leverages the difference in micro refractive index of the sample to create high contrast image of transparent specimen. But in phase contrast, the image contrast is the technique used uses a phase plate to create constructive and destructive interference, which enhances the visibility of small colorless structure. So to enhance the image contrast, it is done mainly by two ways. The first is that by generating a constructive interference between the scattered and background light rays in the region of field of view that contains the specimen. And the second way is to reduce the background light that reaches the image plane. That's how the image contrast is enhanced. Then it is particularly useful for imaging living cells, cell division. That kind of a dynamic process can be observed with this contrast microscopy. Here, a example has been given between bright field and phase contrast. There is another technique called fluorescence microscopy, where as we all know, excitation simple fluorescent molecules. It is excited by a specific wavelength of light, uh, and when it de-excites, it emits certain light at a longer wavelength. This emitted light is then detected and used to create a high contrast image of fluorescently labeled structure. And specialized filters are also used to separate the excitation and emission light. Uh, Desired fluorescence is detected, so that the desired fluorescence is detected. So these are the certain advancement applications in this field, optical microscopy field. Super resolution microscopy, the techniques that can achieve resolution beyond reflection beam of light, revealing nanoscale details. So research has been going on these aspects. Correlative microscopy, combining multiple microscopy modalities to gather complementary information about a sample. Then live cell imaging, advancement in fluorescence labeling, and fast image acquisition enable the study of dynamic cellular process. And certain dynamic processes are also observed by phase contrast microscopy and high throughput imaging. So automated microscopy platforms, rapid scanning analysis of large sample. So that's it from my side. Thank you.